Morning, everybody. Hey, listen, I'm not going to return your exams today. I'll return them on Wednesday. I posted your grades this morning, so you can see them. I'll get them back to you on Wednesday, and I'll post the solutions. I also do want to point out to you that the next exam is on Monday, May 1st. It doesn't seem like it seems far away, but it's actually not, because we have spring break and Eastern holidays in between. So we're sitting right here on the 3rd, so we don't have that long until the next exam. It'll cover the end of the chapter on lenses, and then we'll have a chapter on diffraction and interference, and then we'll get a little bit into sound. Okay? All right, so we're pushing on the home stretch. For your grades that I put up, just a couple of things. Over here. Oh, sorry. So the grades that I put up, I have not updated the how to make an A, how to make a B business. So like that changes, of course, because now you only have exam 4 in the final. But I haven't updated that. I don't intend to. But if you need that information, let me know. And just let me know if you want that information. Let me know. Okay. And then also, I put your class participation. I gave the maximum is listed on Moodle, so your percentage is out of the maximum. But really, what I say, around about 35 or so, 30 to 35-ish is where you need to be. So if you're there, you're doing fine. Don't sweat it. Just keep coming to class. If you're below 30, you really need to make sure you're coming to class and make sure you're getting as many questions right as possible, because it might mean that you don't get the full 50 points. And then I also put up your tutor assignments, and remember 60% is the threshold that you're cutting for. Most of you, I think, have 60%. But if you're not getting that, you need to make sure you do well on those other assignments. And I'll be posting one soon for this next chapter. We'll probably have 2 more assignments on tutor. Any questions about anything that I've sent you or posted you or whatever? Exam went okay on Friday. Your special guest proctor did okay? You can tell me. She's awesome, isn't she? Listen, what did I make? I made a 98 on my most recent exam. Yes, thank you. It was, It was my heritage class, Baptist Heritage. Let's see, so also what else I wanted to tell y'all? Oh, our team did pretty well. Well, our team sort of came middling, sort of middle of the pack, which I expected. But we had one guy that came in like 28th, and last year he'd come in like 56, which was good. Listen, at state competition, these students, they are wacko. Like they hire tutors, and they're very devoted to mathematics. They hire tutors, and they spend hours a day preparing. So I was really glad for them, and he got in 28th. And then my 6th grader, which they're like no 6th graders because it's 6th through 8th grade, she came in like 50th out of 150, so she was rocking it. That was out of the park to come in, so I'm excited about her, but she's going to St. Joseph's next year. Just take a moment to grieve over the loss of Carly Landry. Okay. Let's look at lenses. You'll see that lenses are going to be very, very similar to mirrors, okay? We'll see 2 types of lenses that we'll deal with. The names of the lenses are similar to the mirrors, but they actually sort of do different things. And I'll explain to you where the names come from. It has to do with the geometry versus what they do to the light. But there are 2 types of lenses that we'll deal with. Those are convex lenses. They look like this. These are also called converging lenses. These are akin to concave mirrors. So if we're thinking about mirrors and lenses and the stuff that they do to light, you'll see that these are a lot like concave mirrors. And by the way, concave mirrors are also converging devices. We have 2 words that we use to describe optical devices: convex and concave, and then converging and diverging. And one of them describes the geometry, the shape of the surface. So convex, concave. describe the shape of the surface. So you'll see that the convex lens, which has this shape to it, it looks a lot like a convex mirror. Like if you forget about this side, it looks a lot like a convex mirror. And that's why it's called a convex, because it sort of bows out like, I don't know, belly or whatever. So convex, concave gives the shape of the surface. And then we'll see converging and diverging. These words refer to what they do to the light. So what the device does to light. Does it make light converge to a point, or does it make it diverge? So for example, if you remember the concave mirrors, you had light came in, and they converged at a particular point. In a similar way, convex lenses will take light that comes in parallel and make it converge to a particular point. These are called concave lenses. Concave because they sort of cave in. And these are diverging devices. These are like convex mirrors. And if you remember with the convex mirrors, you have light that comes into them and they diverge. And diverging or concave lenses will do a similar thing. They'll cause light to diverge. All right, so we have two words we're throwing around, concave, convex. That refers to the geometry, the shape of the surface. Concave devices will sort of cave in like this. So this is concave, and then this is also cave in. And then convex has that sort of bowed out surface that comes out. Convex mirrors are like our security mirrors, and then convex lenses are like these. There are other types of lenses that you'll see occasionally, and they're usually sort of a mishmash of the words. So like plano-convex lenses, this side is convex, and this side is planar. Or, you know, it's a flat lens. And then you can have convex, concave. You probably see the routine now, convex, concave. This is convex on this side, concave on this side. Meniscus, don't worry about the meniscus, you're not going to see that, but it's a lot like the convex concave, but it has a meniscus shape to it. Y'all familiar with meniscus from chemistry. And then plano concave is plano on one side and then concave on the other. You might have a question on the next test where I just show you the lens and I ask you to identify it. It won't be the meniscus, it'll be one of these others, or either just a plain convex or a plain concave. All right. Sometimes the convex lenses like this, or the concave, these are called biconcave because they're concave on both sides, or biconvex because they're convex on both sides. This is a convex lens. I'll pass it around in just a bit when we talk about the images, but this is a convex lens. You can see it sort of bows out on either side like that. Bigger in the middle than it is on the edge. Concave lenses, you ever know anybody, my wife is one, who has glasses that are really thick on the outer edges? Right? Y'all are one of those people? Or, yeah, okay. So those are because you have diverging lenses in your glasses. Those are concave lenses because they're thicker on the side than they are in the middle. Although these days they have special glass that the optometrists use to make them a lot thinner than they are, and that's what she does. So don't go looking at her glasses because they look normal. She's a little sensitive about it. They're very thick. Coke bottle glasses. That's what they used to call them. Coke bottle glasses? Yeah. But they're thinner now. They do a lot better job. Okay. We're going to define our focal length. It's defined in the same way as for mirrors. It is the half the radius of the sphere. Just like we had for mirrors. From which the lens was cut. I'll put that in parentheses because in a similar way as we thought about mirrors, how we had this big sphere and then we just cut a piece off of it and it's spherical on one side or the other, we can think about lenses in the same way. Though of course you know when they make lenses, they pour glass, molten glass or plastic into a mold, and then they can come back and shape it and polish it and make it exactly the shape that you want it to be. But we can think of it as it being cut out of a big sphere. So for example, this is how what type of lens is this? If this is the lens that I'm talking about, is that a concave or convex? That's a convex lens. It looks like a convex mirror. And so if we have this, our center of curvature is right here, and our focal point is equal to half the center of curvature. So there's our focal points right there. Also notice there are other focal points, but these would be for lenses over on this side. But for this lens right here, those are its focal points, and those are its center of curvature. Also notice that each side has a different focal point. We didn't have that with mirrors because they just had one side. But with lenses, you can have two different focal points. But that doesn't happen very often, so we'll assume that our lenses have the same focal point on both sides. But if you go into some upper level classes where you're dealing with light, you might see lenses where they have, two focal points. But I don't know if I've ever seen a lens with two focal points. So we'll assume that our lenses have the same focal point on both sides. And that just means that the curvature of both sides is the same. It's, cut from the same sphere. All right, let's see. A lot of this is going to be the same, so hopefully, if you got mirrors, then you'll get lenses pretty easily. We'll see some slight differences. The focal length, we can define it by the center of curvature. We can define it as c over 2, but we can also define it based on what it does to the light. And so a converging lens will make light rays that are parallel focus at the focal point. And then also for a diverging lens, I have light rays that come in. They're not going to converge. Instead, they're going to diverge because that's what diverging lenses do. But they'll diverge in such a way that if you trace back the rays, we've seen these types of rays before. We call these virtual rays. They'll trace back to the focal point. I'm going to say this again later. Let me go and point it out here because this is different with mirrors. Remember with mirrors, we had, in all the mirrors, like say if we had a concave mirror, we called this the real space, and if we had an image on this side, it was real. And then we called this the virtual space, and if we had an image on that side of the mirror, it was virtual. And you can sort of think about it that if I have, an image on here, then that's the image I can project onto the screen. But if I have an image over here, I can't project it onto the screen. And that's how we define real and virtual images. But it's different with lenses. With lenses, this side is the virtual space. So anytime I have an image on this side, it's going to be virtual. And anytime I have an image on this side, it's going to be real. Now, how do I define the sides? Well, I generally define the sides by the path of the light. So the light is coming in this direction, so I'll call this the side where my virtual image is, and this the side where my real image is. And that's sort of how lenses work, right? Like you consider the projector up here, there's a lens, there is a bulb behind it that projects onto the lens, or that shines onto the lens, and then this is the image. So you have object, lens, image. Object, lens, image. And that's sort of the normal way of doing things when you get a real image. Object, lens, image. But sometimes you can have object, image, lens. And when you have that scenario, it's actually going to be a virtual image. That'll come out when we're working things, so don't sweat it right now, but I just want to point that out. All right, so let's look at magnification. Magnification is exactly the same as what we had with mirrors. It's minus Q over P, and the sign conventions are the same. So I just repeated them here. If I have a magnification that's bigger than 1, the image is bigger than the object. If it's less than 1, it's smaller than the object. If it's equal to 1, it's the same size. If it's positive, it's upright. If it's negative, it's inverted. I think I probably got this right. Y'all okay with this? All right, good. It's exactly the same as it was for mirrors. And in fact, the lens equation looks a lot like what it looked for mirrors. 1 over F, it looks exactly the same. 1 over Q plus 1 over P. So for example, if I have a convex lens, this is my object. It's going to turn out that this will be my image. which we'll show with our ray diagram soon. You'll see those again. They'll be similar. This is my value for P. This is my value for Q. Is this image going to be real or virtual by what we talked about? This is a real image. It's like the projector up there. So if I put a screen right here, then I would be able to see the image. Whereas if I have an image over here, then that's going to be a virtual image. But see, I'll pass around this lens. Y'all have done this in lab. Many of you have. I think everybody that's in lab has done it. You can take this lens and make an image. So you want to like make an image of something that's fairly bright. So if you're underneath a light, or you can sort of angle it, then you can make an image of the light, and it sort of depends where you are, and you can see the different light bulbs that are in the picture. So you can do that. That's a real image. But you can also use this as a magnifying glass. You know, I've done the optical instruments lab where you make a magnifying glass. You know, like that. Maybe like that. Anyway, you can use it as a magnifying glass like this, and that's going to be a virtual image. That's not an image that you can put onto your screen. And the difference is where the image is with regards to the focal point. So the focal point of this thing is right about here somewhere. If you're inside the focal point, it's going to make a virtual image. That's just like for concave mirrors. If you're outside the focal point, it'll make a real image. So like when I hold this up a good distance away, I can create an image. So take this lens, I'll pass it around, make a real image on your desk or book or whatever, and then also you can make a virtual image just by looking at it like a magnifying glass with your finger or whatever I look at it. That's a virtual image. Okay? So our sign conventions, I've already mentioned this, but they're a little bit different. Our object distance is positive if it's in front of the lens, and it's negative if it's in the back of the lens. And so what I mean by that, how can you have an object in back of the lens? Well, we'll see that a little bit later when we get to two-lens system. It's a little bit funky. But imagine that my object is over here. My light rays are traveling in this direction. And the side on which the light rays are propagating, I consider that to be in front of the lens. And then the other side, I consider that to be in the back of the lens. So if my object is over here, it's positive. If it's over here, it's negative. So this would be a positive P. This would be a negative Q. Or excuse me, not negative Q, negative P. But it's different for images. So my positive image distance is going to be over here, and my negative image distance will be over here. And so that's what this table is trying to convey to you, that if I'm in front, if my image is in front of the lens, that's like the magnifying of your finger or whatever you chose to do, that's going to be a virtual image, so it's going to have a negative image distance. If it's behind the lens, the image is going to be positive. If my object is in front of the lens, this is sort of the usual way, and it will almost always be this way, at least in one lens system, it will always be this way. P is positive. If the object is behind the lens, it'll be negative. Okay? Let's do this quick test. All right, let's see. The focal length for convex lenses is positive, and for concave lenses is negative. Remember, these are diverging. These are converging. I know that with mirrors, we saw that concave mirrors had a positive focal length, but those were diverging mirrors. So that's the difference. If it helps you to think about these as converging and diverging, that's okay. They're similar in the focal point and how that works out. You understand what I just said? Let me repeat that. So, concave mirrors have a positive focal point. Concave lenses, on the other hand, have a negative focal point. Convex mirrors have a negative focal point. Convex lenses have a positive focal point. They're switched. Okay? But you can think of it as, in terms of converging devices, always have positive focal lengths. Diverging devices always have negative focal lengths. Dylan's really excited about that. Are you excited? No. Okay, let's try this question. This is just, you're using the lens equation. Here I tell you what type of lens it is. I tell you the magnitude of focal length. You need to determine is it positive or negative. Give you the object distance, and I just want to know what is the image distance. And is it to the left or right of the lens? Go ahead. Let's go about 10 more seconds. I'll stop at 140. 140. All right. Feel free to ask your neighbor what they put. Okay, I think A is right. Let's see. So here my concave lens, it has a focal length of 10 centimeters, but because it's concave, it's negative. And then the object, P, it's located at 10 centimeters. So if I'm looking at my concave lens, my object is over here. Focal point is here and here. Actually, it looks like it's located at the focal point. And then I can calculate Q. I have 1 over negative 10 equals 1 over 10 plus 1 over Q. That's negative 2 over 10 equals 1 over Q. I subtracted 1 over 10 from both sides, and that became negative 2 over 10. That's negative 1 over 5, so Q is equal to negative 5 centimeters. So I know it's 5 centimeters. If it said to the right, that would be wrong. It has to be to the left of the lens, because it's going to be on the same side as the object. So my object is here. My image is going to be here. That's my image. Notice that virtual images, this is a virtual image because this is negative. Virtual images are always upright, just like we saw with mirrors, and for the same reason. M is negative Q over P. If Q is negative, M is positive. All right, so I drew it in that way. And then I also know, I went ahead and drew it at half the magnification, because I know that the magnification is negative Q over P. This wasn't in the problem, but it's negative Q over P. So that's negative 5 over 10, or positive 1/2. So my magnification is positive 1/2. You can see similar questions, kind of like you did before, where you have to know what type of image is being formed by what type of lenses. And we'll go over that with your ray diagrams. That'll help you. All right, let's try one more, and we'll do a few more quicker questions. Your eye is different. Like, your eye is quite different from basically all the optical instruments that we have, because most optical instruments that you have, microscopes and cameras and the like, they change either the object distance or the image distance. Now with your eye, you can change the object distance, right? You can have something here, you can bring it up close, and that changes the object distance. And you can do that too, like with a microscope, right? You can take that little table, I think, I've never used a microscope, but I think you can take that little table and move it up and down, is that right? Yeah, so that changes the object distance. You can also change the image distance with a microscope. You can move the eyepiece up and down, and that changes the image distance. But you can't change the focal length, not without actually changing, the inner workings of the microscope. But the human eye actually changes focal length. Did y'all know that? There are little muscles in your eye that change the shape of the lens in your eye. So when you want to look at something far away, it has a certain focal length, and then when you shift, like almost instantaneously, it changes the focal length so that you can focus on that thing. It's really quite remarkable, I think. Don't y'all think that's remarkable? It's pretty amazing. It's like one of my favorite parts of the body, the eye, or the ear. I'm not sure what I like better. So this deals with that a little bit. Let's try this question. How does your focal length of your eye change when you're looking at something far away and then you bring it up close? How does your focal length change? Does it increase, stay the same, or decrease? It's not D, it's either A, B, or C. What happens to the focal length of your eye? It is a convex lens in your eye, by the way. So it does have a positive focal length. You can think about this in a couple of ways. I know that 1 over F is equal to 1 over P plus 1 over Q. What happens when I bring something up close? What happens to F? All right, let's see. Stop at 125, 125. Let's see, is that right? I always have to think about this. I think that is right. So let's see. What we're happening is the image distance stays the same. So this remains constant. That doesn't change. And so I want to know what happens when P decreases. And what happens when P decreases is that F must also decrease in order for that equation to still be the same. We'll come back to this for images that are formed with our ray diagrams, and it'll make a little more sense, and we'll talk about that a little bit more. Let's try this one as well. I'm not saying anything. My lens still out there somewhere? My stuff, my lens out there? You have it perfect. That's okay, you can hang on to it. It's very interesting. All right, let's kind of wrap it up in about 15 seconds. One 125. A few more seconds. Okay, good. A is right. Everything all right back there? Okay. So a person uses a convex lens. First thing you want to realize is that the focal length of a convex lens is positive. It forms a virtual image 20 centimeters away. That tells me my image distance is negative 20 centimeters. And I want to know the magnification. What is the magnification? Well, it asks for the magnitude, but I already know the magnification is positive because That's what virtual images are. They're always upright. I know that my magnification is negative q divided by p. I need to know what p is, so I can find p as a 1 over f, that's 1 over 10, equals 1 over negative 20 plus 1 over p. And then I solve that for p. 2 over 20 is 3 over 20 equals 1 over p. So p is, what's that, 6.67. And then my magnification then is negative 20 over 6.7, which is about 3. It is 3, actually. It's exactly 3. All right, A is what y'all put. Did y'all do well on the previous one? Oh, did I give y'all a joke for that one? No, I'm sorry. So, this isn't really a joke. It's just sort of a thing that happened to me. This weekend, we were making enchiladas. You want to make enchiladas? Love those things, like cheese and stuff on them. And we're using a thing to slice up the cheese. You know what I'm talking about? One of those boxes of slice the cheese. I cut my finger on that thing. But I think I have a greater problem. Yeah, thanks a lot for ruining my joke, my story. All right. Let's see. Let's do a few more quicker questions in the back. We should have some left over for lenses, I think. Oh, we didn't do all of these, but we're going to skip over these that are mirrors. When do we get out of here? 11:40? So why don't we come back to this on, what's today? Monday, on Wednesday. So we need to do evals. Okay, so let's, we'll wrap up right here. I need a few minutes